Hi, everyone. Welcome and thank you for joining us. Today we'll be talking with Klaus Sutner from Carnegie Mellon University, and we'll be discussing topics related to the undergraduate education in computer science departments, how this relates to computational mathematics, mathematics education in general, and at times computational thinking and other sorts of collections of ideas that are in this space. So thanks everyone for joining us, and Klaus, it's a pleasure to have you here.
Thanks for the introduction. So what I'll be talking about mostly is a course that I developed, oh boy, over the last 20 years or so, called CDM, Computation and Discrete Mathematics. And I'll show you some examples of where computer algebra is used critically in the course. But before I do that, I'd like to give you a little bit of a historical background of how Carnegie Mellon in particular came to walk down this road. With many perils. So what I'll do is I'll give you a little bit of a background, description of the course in particular and other elements in our curriculum that are relevant to that, and then just try to go through a number of examples, and we'll see how far we get with the example part. So I should warn you right away from the beginning, I didn't make up a demo notebook, but I'm actually using the original notebooks that are used also in the course. So there is a bit missing here because, when the student would see those examples, they'd already have gone through a lecture, they'd have lots of explanations and maybe small examples written out on the board and things like that. So I'll just dump you in the middle. So if there's any question at any time, just ask. It may get a little opaque at some places. All right, so it all started a long time ago in the late 90s. There was a couple of people here at CMU who decided that the time really was ripe to revolutionize the teaching of, well, certainly of discrete mathematics, but actually we thought of mathematics as a whole. And the driving engine behind all that was Dana Scott. And at the time, Andre Bauer was one of his PhD students. He was also there, was Marko Petkovšek, you may be familiar with his book, A is equal to B. And then myself. And in 1992, Dana and I, we spent a sabbatical at Bruno Buchberger's RISC Institute, the Research Institute for Symbolic Computation. And we did some experiments there. Dana taught a course in projective geometry. I did automata theory. And it worked extremely well. It was, a great success story. And so we decided we're going to do the same with introductory math, and in particular the discrete math course at CMU. And so we produced a couple of courses. The first one was called Modern Math. That title was too breezy. So I should say I'm a mathematician, but my faculty appointment is in computer science, so I'm in a slightly awkward position here. Modern Math was way too breezy for our math department. So we renamed it to Programming in Modern Math, just to make clear it's computer science related. And in the end, we caved and called it Mathematical Foundations of Computer Science, which is about as lame as you can make it. And these courses all were completely based on Mathematica. So the lecture slides, the lecture notes, recitations, everything was done in notebook format, even the exams, right? So students would come to a computer lab and work in a notebook to answer certain questions and do computations right there live. And so what happened was that we generated a perfectly bimodal distribution. So there was a group of students who thought this was absolutely superb. It was great. They even told their friends in the math department that they should come and take this course rather than the traditional one. Bimodal distributions have two humps, and there was a second hump that was quite a bit larger. And those were people who were really, really unhappy about this. And I could spend way too much time trying to enumerate all the places where we went wrong. I just mentioned two issues that totally blindsided us because we could not imagine that it was going to be an issue at all. And so the first one that really took us by surprise was, now I know it's obvious, but at the time we didn't, that our CS majors, they are extremely opinionated when it comes to programming languages. And there's the full spectrum from trying to write everything in C to using some fancy, functional language like Haskell or something like that. And they simply instinctively rejected the idea of having to write code in Mathematica. Whatever, that's one of the facts that we encountered. And a little more subtle, but also quite fatal, was the complaint that what the students were asked to do in the course, in all three of these courses, was to learn mathematics. But at the same time, we also forced them to learn Mathematica. And this really threw us for a loop completely, because we were thinking about giving the students this incredibly powerful tool that they could use, and that would help them throughout their years at the university. But it was perceived exactly the other way around. It was an additional burden, and that burden was just unfair and shouldn't be placed on them, and so on and so forth. So yeah, in the end, it really didn't work out. But so Andre and Marco both left, and Dana started thinking very, very loudly about retirement. So I decided I needed to change things.
Yes,
Just change the mode of approach. And what I did in the end was to focus on an upper level course rather than the introductory courses. So the current introductory course still has the remnants of our foundational sorry, let me just go back here. The Mathematical Foundations of CS, that's still the current name of the introductory course. And it still has remnants of the structures that we built at the time, but it's sort of been drifting back towards a more traditional math course, much to my chagrin, but I'm just not going to fight that at this point. So what I did instead was to move to an upper level course. And I also grudgingly returned to a more standard course format, which means, there's now the lectures that you expect, Beamer slides, let's say, intermixed with demonstrations with mathematical notebooks. But it looks a little bit more, and the exams are no longer notebooks and so forth. So it drifted sort of back to the more standard format. But in the background, it's all mathematical all the way. So the students who are not sort of fanatically opposed to working with a different computational environment, they catch on their own, and they use Mathematica to do their projects. But there are some others who will insist on writing, C++. And I don't care if you want to waste your time, writing a C++ program that takes you 5 hours and you could do it in 15 minutes in Mathematica. It's totally up to you. So that was a bit of a shift in the face of reality. But it's been working for 20 years. So another idea that popped up at some point in my mind was that if you're trying to rock the boat and change the way mathematics is taught traditionally, psychologically, it's a good idea to have a scapegoat that you can blame for all the misery that we currently have in our math courses. And so I decided Bourbaki was the right scapegoat. So this is a picture of all the greats, in French mathematics. And I think this was the first Congress in 1935. So there's Henri Cartan, André Weil, Dieudonné, and so forth, all the big names. And supposedly, they actually started with a problem that was also related directly to teaching. So Cartan complained to André Weil about not being able to teach Stokes' theorem properly because there were no good textbooks. They were all wishy-washy. There was always an argument at some point: take a wire, make a loop out of it, send a magnetic field to it, and so forth, and that proves the theorem, which of course it doesn't. And so they wanted a real solid foundation for a calculus course, and somehow the project got derailed. The calculus thing was never written, but they started to generate this long sequence of big tomes that were supposed to provide a foundation for all of mathematics. So it starts with set theory, algebra, and so on and so forth. And the project is not dead at this point, but it seems to be on its way out, definitely. The last volume, for example, hasn't been translated into English yet. So, as far as the world at large is concerned, it doesn't even exist. So, this is the sequence of topics. And what's important here to realize is that Bourbaki, in some sense, was a huge success story because it took over math education on the whole planet. So when I went to university in the 70s, I didn't know it at the time, but our curriculum was really completely influenced and structured by Bourbaki. And this has not changed to this very date, really. The structures are still everywhere. And to my mind, that's a big detriment. It just doesn't work in the classroom at all. Now, to be clear, these are not meant to be textbooks, right? But they're meant to build this big structure, this big sandbox in which you can play mathematics. But the basic ideas that they percolated all the way down to high school mathematics, where they cause damage. And so, what are the problems with this Bourbaki approach? One of the issues that are absolutely fatal for computer science majors is that they really don't deal with logic. And it's a tragedy because, this work started in the 1930s when modern mathematical logic really took off. But Bourbaki decided they didn't need any logicians on their team. So they invented their own system, which is a total catastrophe and really inappropriate. They don't care about problem solving, which of course in the computer science curriculum, right? You don't do problem solving, that's death right there. They absolutely do not care about combinatorics. So that's the slums of topology. We don't deal with that. There are no algorithms anywhere. It's nothing, right, in any one of those books. And you don't worry about applications. So there's this whole idea that the only thing that needs to be exposed is the pure abstract theory at the most abstruse level. And that's where their efforts went. They also had this incredibly insane idea, really, of presenting the whole work as a structure that is completely independent of external references. So they don't quote anybody else. It's all Bourbaki, Bourbaki, Bourbaki. And of course, nowadays in the days of the web and wiki and all that, that's insanity. You can't just be an isolated structure. And then the last issue that really is a complete fiasco is they don't have pictures. Pictures, in their mind, detracts from the actual pure mathematics, which of course is complete nonsense. It's exactly the other way around. It's the pictures that lead you to those abstractions. So leaving them out is just insane. So, the battle cry then was, I'm going to fix this all. We're going to build a course that addresses all these issues and does a much better job at getting the message across. And so in order to have a real battle cry that would get people upset on the other side, you can see I'm constructing this image here of two parts, of two groups that are sort of at loggerheads with each other, which is not totally, it's not totally fair, but it's not totally unfair either. Anyway, so I came up with this idea to just tell the people that I think digital computation is the most important development in mathematics in the 20th century. And if you say that out loud, giving a talk in a math department, things get very dicey at that moment because you're obviously, intruding greatly into the territory that's sacred to the mathematicians. But it's a provocation, it's a deliberate provocation, but I actually think it's also, it can be defended in a very reasonable manner. So, 100 years from now, if people look back at what was the important breakthroughs, I think being able to perform large-scale digital computation is going to be really the big issue. And
your courses. Sorry to interrupt.
So, my favorite computer, I had a whole lab full of those. Actually, so I realize now that one needs to explain what this is. It's the next computer, right? It's the legendary computer that Steve Jobs built, and at the time it was. Decades ahead of the competition. Anyway, so the idea is computation and digital computation. The fact that you can really do it, that you can run the code, that's the big breakthrough. That's really what changes things.
Yeah. So
whenever you put out a naked provocation, it's a good idea to have a couple of very broad shoulders that you can hide behind when the arrows start flying. And so I have a couple of quotes that I can always flash up. So one of my favorite ones is Bill Thurston. Who dispels this idea that when you use computation in a math course, you are actually effectively dumbing down the course, right? So that's always implicit in a lot of criticism that you get. And so Thurston, just says, no. You have to understand that what mathematicians consider to be a standard of a valid proof, that's much mushier than what the computer science people do. Getting a program to run and showing that a program is correct is much harder than a mathematical proof. So of course that's fighting words, right? But Thurston can pull it off because he's a Fields medalist, and he used computation a lot in his studies of low-dimensional topology. So he knows where all he speaks. He understands the mathematics very deeply, but he also has an idea of what it means to write all the programs that he used in his research. So that's a good starting point. And then there is Vladimir Burbaki, I should say the late Vladimir Burbaki, who's also a Fields medalist. And he had this experience, I think it was 1990 or so, when he wrote a paper. He was a rising star at the time with a big theorem in it. And then a couple of years later, somebody else posted a counterexample on the web. And it was this really awkward situation where the counterexample it really contradicted the theorem. But on the other hand, no one was able to find the flaw in the proof. So it had to be wrong, but nobody could point at the place where it was wrong. And on the other hand, there was this counterexample. And so Burbaki said, well, the paper that he wrote fell into disuse. People didn't take a position one way or the other. They just didn't mention it anymore. And he became really upset about this. I mean, he made a mistake. He was convinced that, in fact, his theorem was wrong. And so he turned to proof assistance and theorem proving to verify all his work. He didn't, the fact that he had this one wrong theorem wasn't no problem because he still got the Fields medal a couple of years later. So, but he took this sort of as an indication of a crisis when even, the best mathematicians or the best mathematical minds cannot determine whether a proof is correct or not. We need to do something about it. And the answer, of course, is to use computation, right? To use theorem provers and proof assistance and the like. And he actually said, a couple of years ago that he thinks that all of mathematics will ultimately go that way. Everything will be done with theorem provers and computer algebra. Everything will be algorithmically supported. That may be wishful thinking, but we're certainly moving in that direction. And if you look at the computer science side of things, there's Bruno Chassel is always a great example. So he also has this idea that you should think of computer science now pretty much the same way as you would think of mathematics in, let's say, the 19th century, which is this this fundamental core discipline that radiates out everywhere else. So there's mathematics in physics, obviously in chemistry, in any kind of science, there's mathematics, but by the same token, now computer science invades all domains. So you can take just about any area of discourse, and then you put computational in front of it, and now you have a new field. So there is, for example, computational anthropology. So it's everywhere. So all strong endorsements of doing things very, very differently from the approach that Bourbaki took. And how do you actually do this in a real course? Well, it's not so clear, right? And over the years, I've come to sort of filter out a couple of basic requirements that you have to satisfy if you want to transfer a more traditional mathematics course into something that is based on computer algebra and computation more generally. And this list used to look very different years ago, but I'm now convinced that you have a document-centric user interface, where you can do computation and visualization and all that. It's really critical in the classroom. If you don't have that, you're dead from the start. Also, what you should have in place is some system that makes it very, very easy to cooperate, to share information, to work jointly on projects and things like that. There needs to be somewhere underneath a really good prototyping language that allows you to translate your mathematical ideas into actual computations with very little overhead, right? So you don't want to spend time on writing complicated programs or implementing complicated algorithms in order to test out your ideas in a computational setting. So whatever system you use, it has to provide that automatically. It's also really nice, and this has certainly changed greatly over the last 30 years, to have a system that has a great many algorithms built in, right? And so of course Mathematica does exactly that. you don't have to bother if you want to use a Germer basis algorithm somewhere. It's built in, right? You don't have to waste your time by reinventing the wheel and writing lousy software that somebody else can do a much better job at. And in contradiction to Bourbaki, who doesn't like pictures, pictures are critical. So there has to be strong support for graphics. Otherwise, at least for classroom applications, it just doesn't work at all. And then the last item that's sunk to the bottom, it used to be higher up. You would really like to have a connection to a proof checker or a theorem prover. So a while ago, we had our own system called Analytica, but it's turned out that maintaining a separate theorem prover is just way too much work. The payoff just isn't there to re-implement a full theorem prover in Mathematica. So typically now I just send students off to Lean. If they want to do formal proofs, go and use Lean to do that. There's equational theorem proving that's built into Mathematica, so we use that. But if it gets more complicated, then you really have to go to other sources. So that was the list of requirements, the wish list, if you will. And so currently, well, okay, so I've been doing this now, this particular course for 20 years. So I'm sitting on a huge mountain of material, but a semester is still 15 weeks. And so, whenever I teach the course, which I actually will do this for, then I have to pick a couple of topics, and I always start with computation because that's really a sore spot. Surprisingly, you would think in a computer science curriculum it shouldn't, but it is. And in particular, what I like to do is I'd like to advise the students, or guide them towards the notion that Turing machines, which are the coin of the realm, we use them everywhere. Complexity theory, for example, are not really a good model of computation if you try to come to really, to intuitive grips with what computation means. So instead, I do register machines. And in the course, I actually show them a universal register machine. I'll show you, it'll be on the next slide. So, there's a couple of lines of code, and they actually describe a universal machine. And, there's a simulator that I've built, and you can run that universal machine. I'll show you in a couple of minutes. And then we move on to logic, because that's a driving force really behind much of computer science. So, with slight exaggeration, you could say that theoretical computer science is just applied logic. See, so that's first you provoke the math department by saying that digital computation is the most important development in mathematics, and then you provoke the computer scientists by saying that at least the theory part of computer science is just applied logic. So now you have both teams against you, which is actually, so I'm making a joke out of this, but this is actually a real issue when you try to navigate the reality of a curriculum at a university. You need to be aware of that. Anyway, so there's a bunch of logic, and then we dive down to the bottom of the computational hierarchy. We do finite state machines and automatic structures, mathematical structures that can be described in terms of finite state machines. And then in the end, there's a segment on algebra where we do group actions. And I'll show you an example. I explain how GPS actually works as an application of feedback shift registers and finite fields. Mm-hmm. And there's lots and lots of other things, but currently this is as much as I can pack into one semester. And just to have a picture, this is a graphics I stole a long time ago from my friend Buchberger. So he was making an attempt to try to explain what happens when you bring computation into the mix. And so the idea is you have some idea, you sit down, you write a little piece of code, you compute, you experiment, you generate data, sometimes lots of data, you visualize them. And then hopefully after a while, you're going to see some patterns. And once you've seen enough patterns, you can form a conjecture about what's actually going on there. And then the next step is to try to make that conjecture very, very concrete, to formalize it. And once you have a strong formalization, then you go off and prove it in the traditional way. And hopefully so, whatever you've done now wasn't a total waste of time. So you've proven an interesting result, and you can feed that result into the next round, going around that cycle. So you have a new theorem, which will give you a new algorithm, and you can use the new algorithm to do more interesting experiments. Yeah. And of course, this is a gross oversimplification because it's not a nice circle in general. It's more zigzagging around, right? You're trying to formalize your conjecture. You realize you don't know what you're talking about, so you go back to the computation stage. So yeah, it's
Yeah. So
ideally things would
more than
look
a
like that, right? And you just
yeah
wander off into infinity if you go around often enough.
more than a provocation. So
So
you would say that this
the
is really
question,
the
of
thing.
course, is
Yeah.
then immediately if you're trying to make this, a course based on these ideas, a real part of the curriculum, there's always the question, does it work, right? How do the students respond? And the sad truth of the matter is that, Carnegie Mellon, like any other university, is not serious at all about analyzing learning outcomes. We have the usual fig leaves, you have faculty course evaluations and things like that. But this is all very, very weak data. So, whatever I can say that speaks in favor of the success of the course. One point that I like is that there are usually a quarter to a third of the students are math majors. So what has not happened is this effect that people are always worried about dumbing things down to the point where it's just computer science, but it's no longer mathematics. So that's clearly not happening. The course has a reputation of being very difficult, which is fair, but still the FCEs, the course evaluations are very high. Right? So that also means that something happens. And if you look at some of the student comments over the years, that's some of them are quite amusing. I do not know how to make the mathematics of a rock interesting. I have no idea how to do that. And the martial arts reference there, that's this makes no sense unless you know that I used to teach martial arts at Carnegie Mellon. So the undergrads have all these wild fantasies. In fact, there was once a big discussion on the bulletin board about what would happen if I ran into a math professor who has a long career as a bodybuilder. So if we met in a dark alley in the middle of the night, and they had all these theories about how it would work out. The reality is, of course, we would have gone to the nearest watering hole and had a beer together. But anyway, so it's from whatever vague data I have, it seems to be working pretty well. So that's the background, right? It's the idea of trying to really get serious about the fact that we live in a totally different world now in many ways than we did, even you could say throughout the 20th century. We have all these new tools lying around. And to my mind, it's perfectly clear that we're not beginning to make real use of them. They can be pushed much, much further. So, whatever I've said, this is all about discrete math. You could make exact the same arguments about, a course in calculus or differential equations or things like that. The details shift quite a bit, but the basic ideas would be completely compelling the same.
Mm-hmm.
So I mentioned already, oh boy, one of the issues that I'm unhappy about in our computational thinking curriculum is that we follow the traditional lines of defining computability, which means we talk about Turing machines over and over and over again. And the justification for that is that in the end, when you look at the point where computation really pushes down hard on computer scientists, I mean, they have to take a course in complexity theory. That's completely based on Turing machines. And so, you want to explain everything in terms of Turing machines so they get used to the idea of organizing computation with these little devices. And I understand the reason why we're doing it, and I think it's still a great disservice. You can do much, much better by using a model that's much more intuitive, and in particular, intuitive to computer science majors. Namely, you construct a very primitive assembly language, and then you express all computation in terms of this assembly language. And so, formally, these devices are called register machines. And the language they use is completely trivial. So you think of having a bunch of registers that can contain natural numbers. So, 0, 1, 2, 3, and so forth. Mm. And the number of registers is fixed. And now the only operations you can perform in this very, very weak language is you can take the contents of a register and increment it. And then when you're done with that, you continue execution of the program in line K. So this inc sk means increment register the number S, and then continue execution of the program in line K. So add one, and then there's a second instruction, decrement RKL. So this is a conditional thing. Oops, this should be an S, I'm sorry. If you look very carefully, what looks like an R here on the screen is actually an S. Can you morph it automatically? So you look at the register, you check whether it's currently positive or not. If it is, you decrement it. And if not, you do nothing because we only use natural numbers here. And depending on whether the thing was 0 or not, you continue execution in line K or you continue execution in line N. So that's the second instruction. And then the last one is halt. Right? And so the big advantage of this is that anyone can immediately understand, certainly every CS major can immediately understand how these programs work, right? You can just increment, you can decrement, you can stop. That's it, nothing else. So it's extremely straightforward. And it also gets you around coding issues because you don't have to worry about how you express the input on the tape of a Turing machine. Everything is just a natural number, right? So you can do addition, multiplication, you can go through the whole panoply of basic number theoretic functions, and you can implement them with register machines. And it's very intuitive, and it's the cognitive burden is very, very small. And so one very nice feature of the register machine approach, as opposed to Turing machines, is that you can actually explicitly write down machines that do something interesting. So, for example, here's a flow chart for a register machine that takes as input some number X, and then figures out if you write that number X in binary, how many ones are in the binary expansion. And so I don't want to go through this. You can.
Yeah, as I understand,
there's
you've
only
got
three
examples
instructions, right? So one of them is the halt instruction.
Yeah.
This is where everything ends. And other than that, you have only increment or decrement. Well, if you do an increment operation, there's only one thing you can do, and then you continue somewhere else in the program. So this is a node without degree 1. But if you do a decrement operation like this guy here, well, there are two possibilities. Either the register was already 0, in which case you do one thing, maybe you go over here, or if it was positive, you do something else, maybe you go down here. Right? So you have a very simple diagram where every node has out degree either 1 or 2, depending on whether it was increment or decrement. And then there's one place where there is no out edges, namely the halting state. But it's totally straightforward.
So as I understand,
Doing
you
this
also
with
have
a
some
Turing
examples.
machine is already a mess, because organizing counting functions is not so easy to do. But here it's very simple, and you can visualize how the machine works. I'll show you in a second. And so the ultimate challenge always is when you have a computational model is to show that there's a universal machine, a machine that can simulate all the other machines. And with Turing machines, this is a nightmare because universal Turing machines are extremely complicated. And even Turing himself made a mistake in his famous paper. The machine that he first wrote down wasn't quite right. It was not hard to fix, but it was wrong. And so here's a little 13-line, well, actually 14 if you count 0, a little register machine that can simulate any other register machine. But in order to be able to fit this so nicely on one slide, I'm cheating quite systematically. I have added a few instructions, macros really, that aren't in the language. Right? So there's a copy instruction, there's a write instruction, a read instruction, pop, and so forth. These are not there, right? These are higher level constructs. But it's very easy to verify that this copy instruction could be rewritten as a small register machine where you really use the actual language. And on the right-hand side, there's an explanation of how this thing actually works. And this produces a whole bunch of very wholesome projects that the students can work on. For example, you have to show, or a reasonable challenge is to show that this allegedly universal machine here really is universal. Prove it. And that requires quite a bit of argument and reasoning, and it's a very good exercise. The machine that I just showed you is really not a register machine. It's a register machine with macros. Okay, rewrite it so there are no macros. Take them all out. Right. So expand all the macros into little snippets of code that do the same task. So you get really a register machine, plain register machine, and try to do this in the most economical fashion. So make the register machine small, right? Try to really push it down to the limit there. And then, there's all kinds of other things. So, for example, you could ask somebody, this may seem like an insane question to write a simulator for register machines. Well, it's obvious how to do this, right? You just execute. It's a small assembly language. You just execute the instructions. But actually, if you look at one of these diagrams here, for example, if you go on the right-hand side, so here is one particular instruction that says decrement y. And if y was not 0, then the next thing you do is you increment x. And then you do the y instruction again, until you finally have y equals 0, and then you go off to the other side. Well, what's really happening is you're emptying out y, and you're adding y to x effectively. So this is really an instruction that could be written more concisely as x is equal to x plus y. Write a program that figures that out, and then replaces this loop by a single instruction. And then keep on doing it until you have a simulation that takes all possible shortcuts, or at least all possible shortcuts is asking for a lot, but at least some of those possible shortcuts. And so you can actually simulate those machines for trillions of steps, because you're not running through the trillions of steps. You have a clever way of abbreviating things, and then things are actually doable. So there was one student a couple of years ago who did a fantastic job at writing a fast simulator. It's like simulating the game of life, right? Anyone can write a simulator for game of life, but if you want to have a simulator that really works well with gazillions of points and over gazillions of steps, then it's real work. Same here. And the core audience is computer science majors, so it's perfectly fine to ask them to write a compiler, for example, that translates a Turing machine into a register machine. So where the register machine simulates the Turing machine. And you can experiment with busy beavers and things like that.
So these are examples of the kinds of projects.
This approach will provide a better intuitive grasp of what computation really is in the formal sense, where you can sort of see at an intuitive level how things work, as opposed to being in the world of Turing machines, where everything looks to be very primitive from a distance. But then when you actually go down into the nitty-gritty and you try to really prove results, it turns out to be really complicated. So, in the complexity theory course, for example, there's this standard mantra, there's this invocation that says, you can construct a Turing machine that does this and that, but you never do it. You never actually construct a Turing machine. You already talk about them. And so here, this is the remedy. We actually build these machines and we can mess around with them. So there's this simulator for register machines that runs in Mathematica, of course. And I want to just show you one example. So this is not dressed up very nicely. You all know the famous Collatz function, the 3x plus 1 function, where you start with a positive natural number. If it's odd, you multiply by 3 and add 1. And if it's even, you just divide by 2. And then the claim is, if you keep on doing this long enough, no matter where you start, you always wind up at 1. Right? So by just applying this 3x plus 1 function over and over again, ultimately you'll get to 1. And so there's many different ways you can translate this into a register machine. I'm just going to use this one here. And so this is really a register machine. No flaky macros. There's only decrement and increment operations, and in the end down here it halts. And this thing computes the 3x plus 1 function. And in a loop, it keeps going until it hits 1. And so, there's this simulator that runs the program. And, it's a trace of a computation. So what do you expect? Well, you get gibberish, right? You get a data dump that tells you this is what happened during the computation. But, in this environment, it's really, really easy to filter out the relevant information, namely what happens whenever the machine is in state 0. So this is what I'm doing here, is I'm filtering out the steps during the computation where the machine is in the first line of the program. And then you look at the register content, and guess what? Right? So initially the input was 3. And then it goes through a bunch of steps, and then the register changes to 10. Well, 3 times 3 plus 1 is 10, right? And then you divide by 2, you get a 5, and then 16, and so on and so forth. Right? So the point here is that now that you have the whole computation, the whole trace as a simple data structure, you can start mucking around with it, and particularly you can try to visualize what these computations look like. And there's many different ways you can go depending on what you're really interested in. So, here's one plot that's perhaps a little more appealing, where you try to understand how two registers hang together. In this particular case, I forget which is which. One is the X register, the other one is the Y register. And you really can see how the computation unfolds. So, you can ask all kinds of questions what these pictures would look like for a particular computation. And then really the place where things become more or less inaccessible in a different model, you can make up a register machine, a universal machine that simulates all others, if you allow yourself to cheat a little bit and use macros.
Mm-hmm.
But then the students as a homework have to get rid of the macros. And so here's let me just use one of those. There's one universal machine that doesn't expect memory to be zeroed out. So this is the macro version, right? This is the one that I showed you on the slide. So it's a total cheat, because I pretend I have all kinds of operations that aren't really there, right? But you can easily enough simulate them. And now you can really at a very tangible level verify that this machine works by taking a small program, a register machine, and then running it, right? So here is a completely idiotic program which just adds 1 to a register. And the reason I'm using the really small one is because in order to provide that register machine to my universal machine, I have to code it up as an integer. And in this case, the code number is 160. And by the way, in the course, there's a long explanation how to implement these coding functions. So these are basically Gödel numbers, but in a civilized way. The machinery that Gödel invented is exactly the same. And then you can do fantastic things like checking with our universal machine here that 11 plus 1 really is 12. Right? So, what you really need to do there is, of course, then go into looking at the trace more carefully and see how the universal machine really has gone through a bunch of steps. And this is not, I'm not cheating. How about 17? Output is 18. Right? So this is what I think of as a correctness proof. We now know for a fact that the machine works and the simulator works. But so I'm only kidding halfway. To really give correctness proofs is an excellent exercise, and it's quite difficult. You have to do all kinds of inductions, and it's very nice for the students to be able to actually get their hands on these devices. They're not just some abstruse concept that floats around somewhere, but you can actually build them and you can work with them.
Mm-hmm.
So that's the initial part where, since the whole course is supposed to be about computation, we actually give a civilized definition of computation, and then you apply it from there on in other parts. And so in a sense, this is the abstract theory of computation, but made fairly concrete as far as you can make it concrete. Now, the next step is going to be to actually go all the way down into the weeds and do computations that are really, really concrete, efficient, and fast to execute. And so the way it's organized in the course is I talk about finite state machines for a while. So finite state machines are one of the big success stories in computer science, because they are the right conceptual tool to describe all kinds of systems. Like your Coke vending machine is the inevitable example, or tools in Unix like grep or so, where you search for patterns in files and things like that. So this is eminently practical, and the way it's organized again is to try to push the students into an understanding that at least a big part of discrete mathematics directly translates into a bunch of corresponding algorithms. And the algorithms then, can be used to explain discrete mathematics. Right? So, a finite state machine is a really simple model of computation. Everything you can imagine, you can actually implement with finite state machines. And then once you have those algorithms implemented, you can use those to study the machines in greater detail. Right? So there really is a feedback loop where the results of your previous ideas produce new algorithms, and the algorithms then help you to come up with a deeper understanding and more complicated ideas. And so, oh boy. Well,
Yeah.
let me
So
just continue with the slides here. So one of the issues that one finds typically butchered in a lot of approaches to finite state machines is the issue of minimization, right? So it's a big theorem that says if you have a very simple finite state machine, a so-called DFA, a machine that's deterministic and has a unique initial state, then you can minimize them. You can eliminate useless states and make the machine as small as ever possible, right? And there's an algorithm to do that. So if somebody gives you an inflated machine, you can ship it into the algorithm, and what comes out is then the optimum machine, that solves a particular problem. And the way it's handled traditionally, of course, is you just talk about equivalence relations, and then you talk a little bit about how to compute on equivalence relations, and that's it, right? So what we do instead is, just to give you an example, this is half a page taken from the Bourbaki sets volume, where they define essentially equivalence relations. But you can just look at the image. You don't even have to bother to read it. Just, relax, go into a state of no mind, look at it, and you will immediately hate it, because it's the way that the information is presented is just really, really difficult to absorb, right? It's very hard to read. Now, I will admit that this is not what you find in a typical discrete math textbook, but it's not that much different either. This is exactly the definitions that you will find in a standard book. And it's just hard to wrap your head around this stuff. And so what we do is we actually sort of fully embrace the abstract part of equivalence relations first, but then we drill down into some concrete algorithms that are based on that. So, for example, the first step is to say, if you'd like to compute with an equivalence relation, you can translate that problem into something that's much more amenable to a computer science approach, to an algorithm, and a computer function instead. So you have some equivalence relation, and in order to describe that equivalence relation, you find the right function so that two elements x and y are equivalent if and only if that function agrees on x and y. So if f of x is f of y, then x and y are declared equivalent, otherwise they're not. Right? Mm-hmm. So if you give me a function from any domain A into any domain B, then I can always use this to produce an equivalence relation on A, right? Because two guys are equivalent if they have the same value under the function. So that's something that's obviously you can do very easily in the program. And it's easy to check. It doesn't matter what the function is. You always get an equivalence relation. What's a little bit harder to realize is that every equivalence relation looks like this. So if somebody gives you an arbitrary equivalence relation, you can always represent it as a function. And the simple way of doing this is completely useless computationally. That's why it's interesting for us. So you can just map x, an element x, to the equivalence class of x. Then two guys are equivalent if and only if the same image. And that's completely useless from a computational perspective, because you start with a perhaps simple set A, and then you map into the power set of A. The power set is a computational nightmare. You can't really do this, so that doesn't work. And then the insight is, you don't have to do something complicated. You don't have to go into a difficult set B. You can just replace B by A. You can choose a function that maps elements of A to elements of A, and that describes the equivalence relation. And interestingly, if you want to do this in general, the way you do it in math, that requires the axiom of choice. But of course, for us, we don't care about abstruse sets that have no real tangible description. For us, really, the objects that we're ultimately mostly interested in algorithm are just natural numbers. So this is a slight exaggeration, but not much. Really, we can always enumerate things, right? And so in some sense, you can think of whatever the objects are that you're dealing with. Well, they're just numbers 1, 2, 3 up to n. Right? That's pushing it a little bit, but it's true, right? You can keep a table somewhere that tells you what the number 5 actually really represents. Or it's essentially you're just dealing with integers. And now once you have that idea, and the fact that you can represent the equivalence relation as a function from bracket n to bracket n, Well, now you're just talking about an array. It's a plain old-fashioned array where you, for every I less than or equal to n, you have a particular object x sub I, and it's all natural numbers. It's trivial to implement. And so if you're willing to buy this assertion that without loss of generality, I can think of everything I have to deal with as just natural numbers. Now that means every equivalence relation is just an array, an integer array. And so now, of course, we can compute with that, right? And the computation is very straightforward. What's the obvious idea if you're supposed to pick one particular element in the equivalence class that is supposed to represent the whole class? Well, if it's just numbers, everybody will do the same. You'll just pick the smallest element. You'll pick the min, right? So if you have a bunch of numbers 1 through 100, and some of them are equivalent, for each equivalence class, just pick the smallest element in that equivalence class, and that's what represents the class. And since you can represent everything with integer arrays, that's straightforward to do. You can then calculate with these equivalence classes. And this task of minimizing a finite state machine is easily seen to be manageable in quadratic time. You have an algorithm that runs in up to n rounds, where n is the number of states of your machine, and each round takes n steps, essentially linear in n. And so the total damage is at most n squared, though actually in reality often the number of rounds is much smaller. And so you get a pretty reasonable algorithm to minimize finite state machines by basically just following through with this idea that the axiom of choice translates equivalence relations into functions. And in a very concrete way, right? So, some people object at that point that it's insanity to say the axiom of choice is somewhere over and all you need is a minimum of natural numbers. But, that's really where it comes from, right? And so, you get this connection between relatively abstract mathematical concepts and concrete algorithmic implementations.
So we've seen two examples here
and
of
now,
how
once you have this idea that, an equivalence relation should be a function on the set that you're interested in, now you can immediately tweak this a little bit. So in the original formulation, we say x is equivalent to y if f of x is equal to f of y, right? So that's the most natural way of doing it. But now you could back off a little bit and say that instead of insisting that f has the same value on x as on y, think about following the orbit of x under f. So you compute f of x, then f of f of x, then f of f of f of x. You apply f over and over again. And now if you set things up the right way, when you apply f over and over again, after a number of steps, you'll reach a fixed point. So this doesn't work for all functions, but for the ones that we're dealing with here, that works fine. And now you can get a new kind of equivalence by saying that I don't insist that f of x is f of y. I'm already happy if the fixed point that I get to from x under f is the same as the fixed point I get to if I start my computation at y. So this is a weaker condition, right? It just says you have to apply f a couple of times before you finally get stuck somewhere, and that's what tells me whether the original starting points were equivalent. And guess what? This is just the union find data structure. It's exactly what's being done to represent unions of disjoint sets. That's how you do it, and it flows very naturally from this original representation of equivalence relations as integer arrays. Right? This is just repeated table lookup in an integer array. That's all it comes down to. And if you in the context of finite state machines, this will give you an algorithm that is log linear to check whether two machines are equivalent, whether they accept exactly the same input. And of course, you can plot pictures, right? So here is a very simple-minded way of representing an equivalence relation by just doing it in the most ham-fisted way. And what you get here is a structure that looks like this. And now the problem here is that if you start at, let's see what I cannot. Okay, can you see my cursor? Probably not, right? Let's say you start at the very highest point up there in the middle, right? And you would like to know whether this is equivalent to the point all the way over here on the left. Well, now you have to apply the function not just once, but you have to apply it repeatedly. And you can see that there could be a pretty long chain of steps that you have to take until you finally can come to the bottom here, down the root of this complicated tree on the left. So it's a little bit slow, at least for a lot of the points. And now there's this trick of speeding things up, which it's a programming trick. We don't have to worry about it. You path compression and ranking. And now when you use that additional trick, then the picture I just showed you turns into a totally different one, where the tree gets incredibly shallow. It's just, let's say 1, 2, 3, it has level 4. So in the worst case, if you want to check whether two guys are equivalent, you just have to evaluate that. You have to do 4 table lookups. And so this is almost as good as just doing 1 table lookup. So you can do things very, very efficiently.
We are
And this is
actually
the way,
nearing the end of what we're going to have.
Of finite state machines, of deterministic finite state machines, really should be tested. So,
Klaus, can you
it's
hear me?
all implemented, of course. Let's see. Oh boy.
Yeah, can you hear me,
Pick a
Klaus?
random topic.
I was just going to say we're nearing the end of what we have time for the stream.
Let me just, sorry, if you said something, I didn't hear you.
Yes, I was just going to say we're nearing the end of what we have time for the stream. But I know that we have a lot of.
Something is not right. That seems to be good.
Can you hear me?
I cannot hear you anymore.
Ah. Yeah, we suspected some audio issues on your end possibly. So if you can't hear us, well, we're near the end of what we have time for in terms of our scheduled time. But we will definitely, as we have to cut out here pretty soon, we will schedule a time when we can go through more of these examples, because we actually have a lot more follow-up questions about, you showed many examples about how the that spiral of creativity as you're talking about, where as you're going through these computational examples, bringing an actual computer to the mix really helps bring these abstract concepts to very concrete things. So we suspected there was a little bit of an audio issue here as we had some audience questions that we would like to bring in, but again, we will get those sorted, and we will have to have you back on so that we can go through more of these examples and get to more questions that we have on this topic.
Okay, so now I can hear you again. I'm sorry, I was, for some reason,
Perfect.
my Jabra speaker went off, so I have no idea what he said in the last 2 minutes.
Can you hear us now?
I can hear you very clearly. Yep.
Okay.
No,
So we were just saying that as we're nearing the end of what we have time scheduled, we're going to definitely have to bring you back for more of these examples. We suspected there was an audio issue on your end, as there were a couple of questions that we would like to get to. But yeah, so we'll definitely have you back, and we can go through more of these examples and sort of really drill down onto how does the computation that students are creating by working and modifying these pieces of code relate to these abstract ideas, and what in your experience shows that this is a better approach as compared with sort of a traditional discrete math. But again, thank you so much for joining us, and unfortunately we do have a hard stop as we're getting ready to start another stream coming up, but we will definitely schedule a time where you can come back and we will go through more of these examples. And this is really great stuff so far, and
so
we're really looking.
I've lost you again. This is very strange.